Okay, so now I'm going to speak about hemoglobin, which is the molecule on the red blood cells which helps transport oxygen throughout the body. So basically I've drawn a little schematic here, and this whole structure represents a hemoglobin molecule. So this can see with the 4 boxes. So what the box represents is a porphyrin ring, okay? And then in that porphyrin ring you have an iron Fe2+ bound to it, alright? And this whole structure is called a heme molecule. So hemoglobin has 4 heme molecules, and each heme molecule can bind to 1 molecule of oxygen. So for each hemoglobin you can have 4 oxygens binding to it. Okay, so in your normal heme molecule, you have your Fe2+, which will undergo an oxygenation reaction with oxygen and become bound to oxygen, right? So this is what will happen normally. If you have oxidation instead of oxygenation, you'll end up with an Fe3+. Now, when you have an Fe3+, you get methemoglobin, because methemoglobin is essentially a heme molecule with an oxidized iron to become Fe3+. So now, methemoglobin binds to oxygen a lot more strongly than what your normal heme molecule does. So now, the methemoglobin is going to bind to the oxygen, and it's not going to be as willing to release it. So it decreases the oxygen transport and unloading and offloading in the body. Alright? When you have carbon monoxide in the blood, you still have your normal Fe2+, which your heme molecule is going to bind to carbon monoxide, but this bond is incredibly stable and incredibly strong. So it's not going to release that carbon monoxide anytime soon. So if you have a lot of carbon monoxide in the blood, it's going to start binding to all the heme molecules, and it's going to decrease the oxygen affinity that you have in your hemoglobin in the cell. So they're not going to be able to uptake oxygen and transport it throughout the body. So that's carbon monoxide. It's also just important to note that I've just used each one of these as an example. It's not necessary that all 3 of these things can happen on the same molecule. Okay. And then with regards to the formation of hemoglobin, for second year level, it's just important to note that what the most important steps are and where they occur in the cell. So from the beginning you have an intermediate being formed from succinyl-CoA and glycine, and this occurs in the mitochondrium. And then in a later step you have phosphorin intermediates, and reactions happen there basically, and then that happens within the cytoplasm. And then in your last step you have your Fe2+ being bound to your heme molecule, which occurs again in the mitochondrion. So it's just important to remember those important steps and where they occur.